In this video, we're going to be describing name resolution and scoping rules in Python. At this point, we should already know that in Python, names refer to objects and they're reduced through binding operations like variable definitions or parameters in a function. All names in Python are stored in a set of namespaces. A namespace is a mapping of names to object identifiers. So when a new name is bound to an object, a new entry containing the name and object ID is added to the appropriate namespace. Now, if that name already existed in that namespace, because it's been previously bound, then that entry is modified with the new object ID. During the course of a program, many namespaces may be created and destroyed. However, the text here gives a few example namespaces. The local namespace would include names from inside the current function call. This namespace would be created when the function is called and destroyed when that function returns. So all names bound within the function would exist in this namespace. And this namespace's lifetime is, of course, tied to the function. The global namespace includes names from modules and is created when a module is imported and typically destroyed when the interpreter exits. The built-in namespace contains the built-in functions and names included by Python. This namespace is available as long as the interpreter is live. So, why is it that we have all these namespaces? Well, first, they allow us to more easily create and work with names. Without a namespace, it would be very difficult to use common variable names. If all Python used a single flat namespace, then if more than one block of code tried to use the variable x, for example, then they would no doubt overwrite and interfere with one another, making it very difficult to guarantee correctness. With namespaces, we can actually partition the space of names such that the variable x can have different meanings in different contexts. Another important concept in Python is scope. Scope refers to a textual region in a program where a namespace is directly accessible. Scope is statically determined from the code itself, and then used as needed when functions are called. During the execution of a program, there are at least three nested scopes whose namespaces are directly accessible. When the interpreter needs to find a name, say we want to evaluate the expression 5 times x, the interpreter needs to know which x. So the local scope, or the innermost scope, refers to the code of the current function, and the namespace accessible at this scope is searched first. Meaning for our expression 5 times x, it would first check the local scope for the name x. If that name was not found, then the interpreter would search any enclosing scope that exists. This refers to any enclosing or nested functions, and it includes non-local names, which we'll actually discuss at the end of the notebook. After the enclosing scopes, the global scope is searched, which will include the current module's global names. And finally, the namespace associated with the built-in or outermost scope is searched for the name. Now, name resolution is referred to as the nearest enclosing scope rule, or LEGB rule, as it starts with the local scope, then any enclosing scopes, followed by the global, and finally the built-in. So, just to be clear, namespace is a mapping of names to object identifiers, and a scope defines the regions of code where a particular namespace can be accessed. So let's look at an example. This example labels each scope, or textual region, with the exception of the built-in scope. Each level here prints a statement identifying which scope we're in. It binds a local variable a to a string and then prints that string. For the global and enclosing scopes, we're printing the value of a both before and after a call to a function. We can see that here in the global, and then again in the function test and closing. Now, if we look at the output, we see the string global scope is printed, and then lines 1 and 5 here print the same value of a. This is because scope is defined textually. The print statements need the name a, and so the interpreter looks at the namespace directly accessible to this scope, and it finds the name a here. It doesn't matter that the function test and closing also has the name a, which was set before the print at line 5. Similarly, if we were to move to the call to test and closing, we see that it also outputs a string here describing which scope we're in, and then it does the exact same thing. Lines 2 and 4 both need the name a, which it finds locally. And once again, it didn't matter that test inner also had a name a that was declared before the print at line 4. The local a for test and closing here was used in both print statements. And so if we move to test enter, we see the same thing. And in each scope, the name A was registered with a namespace directly accessible at that scope, and the print statements used the local names that they found. Now let's say we remove the binding of A from test enter and run this block again. Notice that the output is slightly different. The print from line 3 still needed the name A, and that A no longer existed in the local namespace. So the search moved to the enclosing scope to check the namespace accessible from that scope, where it did find an A. In this case, that A was defined here. And so we see that the print for line 3 printed that A instead. Likewise, if we were to remove the A from test and closing and rerun the block, we'll see that the search for each name A had to make its way up to the global scope in order to find an entry in a namespace that matched the name A. Hence, all the outputs here now say A from global. If you recall from the chapter on control flow, we introduced the concept of blocks, which is a piece of Python program text that is executed as a unit. Now, Python allows us to define or bind names anywhere within a block, and all uses of that name within the same block will attempt to use that instance of the name. So let's look at a few examples to see the implications of this. In this code block, we have a function f, which takes the parameter x, and on the first line of this function, we rebind x to the result of the sum of the argument x and h. Now, h hasn't been defined yet. However, on the next line, h is bound to 5. And then finally, the function prints x and returns. Now, because h is used prior to being defined, we should expect to get an error. And if we run this block, we do indeed get an error, but not a name error like we would have expected for using an undefined name. This error is an unbound local error, and it states that the local variable h was referenced before assignment. This tells us two things. One, h is a local variable, and two, it's being used prior to the definition within the local block. So when the interpreter attempts to find the name h, it looks at the local namespace and it finds it, but it recognizes that it has not yet been defined at this point in the function. So we're going to try this again. In the next code block here, we have the same exact function, but we've defined h in an enclosing scope. And so when we run this, one might expect the first line of the function to use h from the enclosing scope and then rebind h here. However, that's not the case. When we run it, we see we still get an unbound local error. So why didn't the line here use h from the higher scope? Well, the reason is scope is determined textually, meaning that the interpreter parsed this function prior to its call, and while doing so, it was building the scope hierarchy and registering names with the appropriate namespaces. And that means when the function was actually called and the line x equals x plus h was evaluated, the interpreter checked the local namespace for the name h and found it, but it also found that it had not yet been assigned a value. Now, because it was found in the local namespace, there's no reason to continue searching for h in any enclosing scope. So this is why we see this particular error. If we had removed the local assignment of h from the function f, as in the following code block here, we see that in this case, h from the enclosing block is used, and now we actually get an output of the sum of these values rather than an error. Scope and blocks actually don't have a one-to-one relationship as you might expect, meaning that not all blocks introduce a new scope. Now we know that a function body is a block and that it introduces a new scope with its own namespace. So if we define the name inside a function and then try to use that name outside of the function, we get an error. But this is not true for a for or a while loop. So if we define the name inside a loop like this actually works. Now in both examples, we define a variable within a block, but in the case of the for loop, no new namespace was created. So we were able to access the variable in the enclosing block. So this shows that blocks and scope are not necessarily one-to-one. And it turns out that there are some that believe that this is an inconsistency in Python's grammar and scoping rules. And I've given you a link here to a recent bug submission on this topic. You can actually find many instances of this topic on discussion boards or even on Stack Overflow, arguing the case one way or the other. But I will say that there are many applications that rely on this feature, and the changing of scope rules for these loops would be a major headache. And actually, if you recall from the Lists Revisited notebook, we described this feature of for loops as a side effect. And then we gave you some examples of ways that you could avoid this behavior if it was indeed undesirable for your particular application. Okay, to wrap up this notebook, I'd like to describe two keywords that allow us to modify in which namespace names are actually specified. And these are global and non-local. The global keyword allows us to specify that a name should exist within the global namespace. Any use of a name declared as global within a block will use the global instance. And if that name has not yet been defined, then it will actually be added to the global namespace. The second keyword is non-local. This is similar to global, except that it causes specified names to refer to previously bound variables in the nearest enclosing scope, not including the global scope. Note that if a non-local name does not exist, then an error is raised. This example contains a function scope test that contains three nested functions. Each of the nested functions assigns a string to the name test A. The string assigned by each tells us which function made the assignment. So the first function here, test local, actually assigns the string local to a local variable named test A. The next function, test non-local, first declares test A to be non-local, and then makes the assignment using the string non-local. Now, because it's using the keyword non-local, this requires that the name test A already exists in an enclosing scope. And so this particular instance refers to this test A declared here. Now the function test global declares test A to be global first, and then makes an assignment using the string global. Now, since there is no global instance of test A, the first time this function is called, it will actually register the name test A with the global namespace and then bind it to the string global here. Now, if we look at the rest of the function scope test, we bind the string test to the name test A, and then we call each one of our functions and print out the value of test A after each call. Outside of this function, here at the end of the code block, we call the function scope test, and then we print out the value of test A at the global scope. Now, if we run this block, we see that after the function test local runs, the value of test A is unchanged, meaning that our scope test function bound the name test A to the string test. The test local function was called, which then created a local variable with the same name, setting its value to the string local. And then once that function returned, we printed out the value of test A. And we see that it used this value here, which was local to the function scope test. And this is because, again, the function test local operated only on a local name test A and not the one from the enclosing scope. Now, after the call to test non-local, we see that this function bound the name test A to the string non-local. And this is because it declared the name test A to be non-local. So the interpreter found the first instance of this name in an enclosing scope and used it. Next, after the call to test global, we see that test A was not modified. It still pointed to the string non-local. And that's because the use of the global keyword here ensured that this bind operation occurred at the global scope rather than the one from scope test. And we can see this in the last line where test A contains the string global. Now the text below this code block actually has some observations that help describe what's going on in the code above, but I would also like to point you to the links at the bottom here, which include more detailed discussions on blocks, scoping, namespaces, and the LEGB rules. And so these are definitely worth a look if you want more information about what's going on in all the examples here.